we stopped at dew point, right? In the last class. So we will continue with boiling point. You have any problem with dew point? I didn't give you any assignment for that, or I have? I haven't.
Heaven.
Haven't. So after I'll finish today, I will give you a bunch of questions to do for multi-component distillations. Okay. So for boiling point, if you can remember what I'll just recap so that I'll refresh your memory of what we have done last last Thursday, right? We didn't have class on Sunday. So this is what you see, or what we've gone through for last Thursday. You have to do this by trial and error. Okay, you have to choose a temperature. Okay, and then you find the K value through this graph. Okay, and then you'll find the alpha value. Okay, alpha value is actually using all this formula. Okay, and then masukkan alpha value. You have to choose a component, usually the heavy key component. Okay, the heavy key is like the major component you will recover at the bottom, and the light key would be the major component that you recover at the top. Okay, and then you will do this. Okay, so basically you will take 0.26 in this case as the K reference, and then you will continue with calculating the alpha. Okay, this is how it looks like for the first example is this, which is to calculate the flow rate of W and D, using the first assumption with all the components lighter than the light key will go or will exit at the top, all of it, and the component heavier than the heavy component will all of it will exit at the bottom. Okay, so at the bottom here. Okay, so that's how you calculate the D and the D and the W. Okay, and then if you remember, this is what we did in finding the temperature. Okay, so because your first trial was already good enough, you don't have to do a further trial or second trial. Okay, so next it's more or less quite similar to what we would do in dew point calculation. So this is for boiling point. Okay, for boiling point is the formula is different. Okay, this is the formula. If for dew point you use sorry, if for dew point this is for the boiling point, so you take the alpha times the xi. If it's for dew point, you take the alpha, oh no, you take the yi divided by the alpha, right? So you have to follow this formula for boiling point, and then you have to calculate the y after that, and the steps are more or less quite the same with what you did in dew point. Okay, so to make you understand this further, you will look at the same example. Okay, this is what you have. Sorry. Okay, this is what you have from the question. Okay, you have calculated dew point, and now you want to continue with boiling point, and then you assume 132 degrees Celsius, and the K value found at this point would be 2, I think 2.0. Okay, and then you calculate the alpha. Alpha is always the Ka for, sorry, this is not this is not the alpha. I tak nampak tadi ni. Oh no, that's my eraser. Mana eraser saya? That's my eraser. Not this, okay, salah. This is salah, tak nampak. Okay, ini the K value at 132 is 1.1. So you take each K value divide by the K reference, you get all this, and this one is divided by itself and all that, and you calculate xi times alpha I, you will get the summation. Okay, now you get the summation, and you will calculate all the yi according to the formula. Okay. All right, so and then you will go, this is what you use. This is what I said about the K value for, this is the K value for pentane. Okay, and then that's all. Do you have any question for boiling point before I go into minimum number of stages and minimum reflux? No? Okay. Then we will go to minimum stages. Minimum number of stages is what you have when sorry, can you please not make noises here? So, Zara, can you please go and see your video kat luar? We are hearing your video tau. Okay. So the reflux ratio at this condition is actually total reflux, okay, which is infinity. At total reflux, you will get minimum number of stages, okay. So this is the equation that you're going to use to calculate the minimum number of stages, and you have all these. Okay, you have to remember, or you have not remember, because you can always refer to this slide when you do your test or your exam, but you have to get the whole of it. Okay, so LDL is for light, D is for distillate. So it's actually mole fraction of the light key component in the distillate. Okay, sama juga dengan XLW, light key component in the bottom product. Ini heavy key component in the distillate. This one is heavy key component in the bottom product. And then you have to calculate your alpha average. So you will have to take the alpha value for the light key component in the distillate and the light key component at the bottom, and times that and find the square root. Okay, so actually the alpha is just taking the light key, not the heavy key. Okay, so and then this is the distribution of other components after you get the finalized minimum number of stages. Okay, so then we'll look at this example, the same example we use. So you have to really label them in this nomenclatures. What do you call, what you call that? Okay, so you have to know that which one is XLD, which one is XHD, which one is XHW or XLW. Okay, so L is light key, H is heavy key. Okay, so if it's XLD, which one is here? Okay, so Y is actually equals to X for the distillate. So you'll take this one. This one is XLD, light key component in the distillate, because this one is for your distillate. This one is for your bottom product. Okay, this one is your top. Okay, so sorry sampai situ. Okay, so you take that XLD. Okay, this one is your XHD and XHW sini, heavy key, XHW, XHW, and then the XLW. Okay, so as for using looking at this formula, you can just cross out the D and the D and the W and put all these values in, as well as the alpha average that you already calculated. What is alpha average tadi? The light alpha of the light key dekat distillate, alpha of the light key dekat bottom. Okay, using those two values, okay, 2.5 and 2.043, you get your alpha L average. Okay, put in all the values in here, then you will get your number of theoretical stages. So remember, this is number of theoretical stages. If it's using a full condenser, then you just have to minus 1. Okay, so you will get 4.4 theoretical trace. If you're using a partial condenser, then you have to minus another 1. That is going to give you 3.4 theoretical trace. Okay, so you have to be careful with this. Look at the type of condenser used and look at the question whether it's asking you for the stages or for the number of trays. Okay, and then for the distribution of other components, you just put in the value of the minimum number of stages over there and put in all the value. Okay, this is for alpha for each component. Okay, you will take the value in the distillate as well as in the bottom product. Okay, so you will be calculating them for all of the components. Okay, and finally you will get all the composition for each. Okay, this is the actual composition, because the first actually what you did is just to see or you assume this in the beginning. You assume that this is 0 and this is 0, but that's not the case. After you have calculated the minimum number of stages, then only you can calculate the actual flow rate. Okay, so this is the actual flow rate for each. From the flow rate, then you can calculate the composition for each. Okay, so normally this is done when you get the minimum number of stages already. Before that, you cannot really you cannot really calculate the actual distribution. Okay, so then you will revise the distillate composition or the flow rate. Okay, this one. Okay, you begin with 0 here. Sorry, 0 here and 0 here, right? But now it's not 0 anymore. Sorry, mana 0 tadi? YD oh here, sorry, salah pula. Itulah, it's quite the same. This is composition, this is the that is the flow rate. Okay, so you begin with assuming those values as 0, but now after you have gotten the minimum number of stages, you actually can put the value into the formula and you can actually calculate the actual or the final distribution of the composition. Okay, all right, so then we will go to the minimum reflux. Okay, our minimum reflux, you will use this formula. First, you have to use the formula for the Q. Okay, 1 minus Q. Alpha is a value that you have to do trial and error on. Okay, after you get this value of alpha, then only you put into the next formula. After you have done the trial and error here, okay, you have to do trial and error there, and then only you put the value in the next formula for you to find the R mean. Okay, so let's look at the example for you to understand this further. Okay, first you have to assume a value or a boil not a boiling point, a temperature between the boiling points and the dew points that you found. Okay, in the previous part of the question, you found the dew point as well as the boiling point. Now you want to take the value in between that, so you plus those two value and divided it with 2, and you will get 99.5. And with this 99.5, then you will go to see the K value. Okay, and from the K value, then you will calculate the alpha value. From those alpha values, you will put them into, okay, these are all the K values at 99 point something that you have calculated as the average or the value in between. Okay, so now what you have to do is use this formula. So if you notice in the slides that I have uploaded in the e-learning, there's some typo here. Okay, because Q in this case is 0. Q in this case is 1. So 1 minus 1 is 0, not 1 minus 0 is 1. Okay, so look at your slides and please correct them yourself. I don't want you to be confused with that later when you refer to the slides. Okay, so now this is the final equation that you want to do your trial and error on. Okay, this is actually xi times alpha I. Okay, so you will do this for your feed, each of your feed. Okay, so this is the alpha value and that is the x value for each of the feed of A, B, C, and D. Okay, so after you have put all the values into the summation equation, so you have to have 4 components, so 1, 2, 3, and 4. Okay, so now you are left with all this theta value. So the theta value is a value that you have to assume. Okay, so actually the value that you want to assume is the value between the alpha of the light key component and the alpha of the heavy key component. So in this case, it's between 2.3 and 1. Okay, so in this case, what they assume first is 1.21. Okay, so put in this theta, you get all this value. Okay, put in that theta as 1.2. You get all those value, get the summation. And what you're looking for in this column is for it to be 0. Because 1 minus 1 is actually 0. Okay, so if you look at this, it gets 1.21. So as it goes, and then first assumption is 1.21, and then it goes down a bit, 1.20. When you go down a bit, you will get a value much lower than 0. Okay, so you go up a bit than this to get a value above that to get a closer value to 0. Okay, so this is just simply as assuming that value. It's not like interconnected between the first trial and the second trial. Okay, just put in the value smartly for you to be able to get finally to 0. Okay, and then after that exercise, after that trial and error exercise, you will finally get your theta. Okay, use your theta to calculate your R min. So put in this into this equation. Okay, and then you will finally find your RM as 0.395. Okay, and then this is another method, not another method. Of course, in the end, you want to know how many number of stages in the distillation column. Okay, so first study you have found the minimum number of stages and mean, and then you proceed with minimum reflux ratio. Okay, and now what you want to know is the number of stages. Okay, so this is the correlation that you will use. This is R over R plus 1 for the Y value, and this is N min over N. So you need to have N min before you use this correlation, and you also need your R min value to calculate this. So there are 3 values correlated with each other here, which is R over R plus 1, n mean over n, and Rm over Rm plus 1. Okay, so this is the equation that you will use, again using the HFLF LWHD. Okay, so let's see from the example as well, the same example. The condition given, the actual reflux ratio is 1.5 times the minimum reflux ratio. Okay, this is what you get from the calculation from the previous part of the question. Okay, and then you will proceed with the calculation of R over R plus 1 to get the value for the y-axis, and then you proceed with R mean over R mean plus 1 to get the value of these to know which slope you want to use, which curve you want to use. Okay, if it's not on the dot, then you have to do some extrapolation, because what you get for your R mean over R mean plus 1 is actually 0.0283. So if you look here, the curve is between 0.3, okay, and 0.25. So 0.283 falls in between. So you need to do some interpolation at the vertical, okay, vertical line. Okay, so and then you calculate your n mean over n. You will get this as 0. No, not calculate. This is from the correlation. So you know your Rm plus 1, you know your R plus R1. So basically you will get that point. From that point, then you will get the value of Nm over N as 0.49. That's from the graph. Okay, and from this 0.49, you can put the value of N mean, and you finally can get your number of final theoretical stages. Okay, -1 if you are using a full condenser. If it's a partial condenser, then you have to -2 for the theoretical trace. Okay, and then after you get the next question is for you to find the feed trace, the tray by which you introduce your feed into, and because you get this n as your, so you have two equations, nm over n as no, not this one. Okay, so you have this equation. Okay, because ne, if you look at this definition, okay, ne is actually mana tadi, number of trays above, sorry, yeah, I'll escape from this for a while to see the definition of NE. So here, if you look at this definition, NE is the number of trays above the feed plate. Okay, NS is the number of stages, not trays, stages below the feed plate. Okay, so if you look at these slides again, all right, so you want to be calculating the feed tray. Where do you actually introduce or put in your feed into the column? Okay, so what you have to use is this formula. Okay, so you already have the theoretical stages to be 11. So that is from the correlation, the Burr and Maddox correlation that you used just now. And you also know this 11 is actually NE plus NS. NE is above the feed tray, NS is below the feed tray. And there's actually another equation, which is this. Okay, so you use the equation of the log to get 0.07344. Okay, so from this equation, you will get finally NE over NS as 1.14, and you get the correlation between NE and NS. Put this correlation back into that equation. Okay, so this is as a function of NS. Okay, so you will finally find NS as 5. Okay, so once you find the NS, you can then find your NE, and then you can answer the question where the feed tray is actually the sixth tray. Okay, sixth tray from the top. Okay, from the top. Okay, so that's basically it for distillation. If you have question, you can ask me, fire away. Any question? Is it understandable? Do you understand what has been covered?